everyone. This is Spencer Snowling from Hatch, and welcome to the GPS-X webinar for June of 2024. I'm glad that you can make it. It's really quite warm and hot where I am, much warmer than I'm used to here in Canada. So I hope you're all doing well and staying cool and or warm, whatever is appropriate for whatever part of the world you're joining us from today. So the plan for today's webinar is we're going to talk about modeling settlers and clarifiers in GPS-X, one of the very most fundamental parts of putting together an activated sludge model. And as I'm going to show you today, we have a lot of different options and different ways of doing things depending on what the task is at hand. And so we'll spend some time going through those. And as usual, I have some demonstrations to show as well. Now, one thing I should mention is this is probably a little bit longer than normal webinar, so we will try and I'll try and keep it inside an hour like I usually try to do. The plan, as always, is that I'll show and do my demonstrations, but if you have any questions that come up to your mind, please enter them in the chat and I will get them at the end of the webinar. If there's enough time, I'll answer them live on air as I usually do, but if we do run a bit long, as I think we might, I'll follow up afterwards with answers by email. Okay, so let's get things rolling. All right, so my plan for today is just a little bit of chit chat about introduction here to settling and clarification, and talk a little bit about the types of clarifier models that we have in GPS-X. That's kind of the one main thing that I want you to be able to take away from today's webinar is we have a lot of different types of clarifier models. So I want you to be able to understand which one is appropriate for which kind of situation. As part of that, we'll talk about why the simple empirical models are sometimes useful, and then sometimes you want to have that more powerful predictive stuff as well, which is our mechanistic clarifier model, the one-dimensional flux model. So we will talk about that in detail. And as always, when I'm talking about individual unit process models in GPS-X, I want to be able to show you the most important things that you need to know to set that up and get it running in your layout and calibrate it. So we'll talk about the underlying settling curves and other things that are there as part of the model. And then I'm going to try to, as much as possible, show you typical ways to display the results in a meaningful and useful way. So I have 3 desktop demonstrations to show you as part of that. And as I mentioned, if you have any questions, please type them in the chat. We'll try and answer them today. If I can't get to them today, we'll put them, I'll get back to you tomorrow with some email. Right. Well, settling certainly is one of the most important aspects of the activated sludge process. So primary clarifiers are there. I've heard them many times referred to as sort of the workhorse of the activated sludge system. They're there to get out all of those organic and inorganic solids that are coming in the raw wastewater. It's a nice opportunity when you use primary clarifiers to get all of that sort of energy-rich COD into your primary sludge and off to your digesters if you're doing cogeneration, if you can. It is also therefore reducing the load to the aeration basins, which require a lot of energy. And so you're looking at being able to reduce your TSS by 50 to 70% and your BOD by 25 to 40%, just basically getting out as much of those solids right off the bat as much as you can. Now, the secondary clarifiers, as you know, are there for a different purpose, and that's to separate out and retain that precious biomass that we've been growing in the bioreactors and bring that back as part of the mixed liquor. And by doing that, you're producing some clarified, hopefully very clean effluent that can go onwards and get disinfected and then head out to your receiving water body. And so those are designed, instead of talking about a TSS removal of 70%, we're talking more about, in this case of secondary clarifiers, capturing almost as much as you can. So that would be looking at upwards of 99% of all the solids going out. So hopefully if everything's working well, you can get, something like 10 milligrams per liter or less in your effluent TSS. So solid separation, of course, is that key part of any activated sludge system. So therefore, it needs to be a key part of any model that you are doing of those systems too. And as I mentioned, we have a lot of different kinds of models of various levels of complexity and sophistication, and they're there to help you do your job efficiently. So it gives you the choice depending on whether you want the model to be predictive and to tell you how the performance is going to be in that clarifier under a range of conditions, or if I don't really care about that at the moment, I'm just going to assume the clarifier is going to work fine, I really need to focus on the aeration system, then you can just set up a simple clarifier model. And so we'll go through what those options are. So when you put a clarifier on the drawing board, you get to select from several different ones that are there in the process panel on the left-hand side of the drawing board. So conventionally, for almost all the time that I've been working on GPS-X, we have had the green clarifiers are the primaries, and so they're calibrated that way. And the blue ones are the secondary clarifiers, and they have a few different options, and they have a different default settling parameters. And so you can drop those on the drawing board. You can grab them from the primary treatment or secondary clarifiers part of the process panel. And as I mentioned, we're going to take a look at both the simple empirical settling models that are there, as well as the one-dimensional flux model, the mechanistic model. I will also mention that the gravity thickener that is also available in the biosolids treatment section, that is in and of itself also a clarifier model. It uses essentially the same mass balance, one-dimensional flux approach. It's just calibrated differently. So I won't touch on it in a great deal, but I will show you how it is similar to the other ones there. So I kind of decided to throw it in the discussion here as well, just so that you are aware of it. You can actually set it up and calibrate it the same way as the regular clarifiers. Okay, so when you put one on the drawing board, if you right-click on the object and go to the very first menu, Models, you will see that you have a choice of several different kinds. This is true for any object that you put on the GPS-X drawing board. Many of the objects only have one model in them, but some do have multiple models, as we're showing here. Now, the reason we have this is that we want to give you some choice out of how much complexity you want in your system. And so there's a lot of times when I want to have a very simple model for simple tasks, and I want to have a more sophisticated complex model for achieving complex tasks. And so that's why you have this different choice here. So I'm going to do a quick summary here about what these different models are. So these names on the left-hand side here, point, empiric, and these WEF ones that are the WEF, TSS-SOR and SOR-SLR ones. These are basically empirical models that have a little bit more sophistication to them. And then we have our mechanistic models, Simple 1D and Mantis 2. Here you'll notice I did refer to No React 1D. That was the old name for the Simple 1D model, in case you're used to seeing that name from days gone by. Okay, so these first three are the empiric models that we have, the empirical models. By empirical, I mean it's not based on mechanisms. It's based on just a regression or a relationship that you are setting. It's a simplification. It is a zero volume settler. That means that we don't actually calculate any derivatives. We don't do any integration of things over time. We just perform some sort of mass balance on the solids going in and out, and it happens instantaneously. So whenever something changes on the way into the model, it changes immediately on the way out. That's not the case for these ones that have volume. There we're modeling the actual residence time of the reactor or of the clarifier itself. So these first three here, these zero volume ones, they're instantaneous. They're nice and easy to use. We have a perfect settler model. That's basically it captures all the solids, or empirical, which allows you to set the capture rate. And then these two are actually ones that we've collected from various places and where they've published models. And these are not setting the capture rate, but the capture rate is determined from an empirical model that's based on these things, solids loading, solids overflow rate, and so on. So that's why these are sort of different from each other. There's, whether you want to use that model or whether you want to set it directly yourself, you've got those options. And then when you get into the mechanistic ones, then you need to set the shape and the volume of the clarifiers. You need to put in all of the, dimensions and so on. And then you have a settling model in there. We have 10 layers. We predict the concentration in each layer, and you get to adjust settling parameters that makes the sludge settle faster or slower. And then you can calibrate the model that way. Now, the defaults option is this one here, simple 1D. That's the one that most people use as the default one that happens when you put it on the drawing board. So just so that you're aware, it is a great model. It's sort of the industry standard that I think all of the simulator products use a similar version of it. So that's the one that our industry has sort of adopted, but you got these other ones here when you need them. Okay, so why are empirical models sometimes useful, right? Like if I've got all of this, modeling power, why don't I just use it all the time? Just turn on all the bells and whistles. Well, the answer to that is that it does take more data and more effort to calibrate those models. So sometimes if I have a specific objective that doesn't require me to have a predictive clarifier model, then maybe that's the way I could go and it will save myself some work. So you have to think about what is the specific objective of your modeling work. I might be doing capacity analysis of the whole plant or individual units, maybe taking things out of service or evaluating a nutrient control scheme or studying how your potential nutrient limitation might affect my plant. These are all nice and interesting process questions that you can answer with GPS-X. In some of those cases, you need the clarifier model to tell you how it is going to perform. So you need it to be predictive. You need to say, when it's loaded up a lot, I need to show that it's not going to remove a high percentage solids as it would as if it under low loading, right? But a lot of the other time, if I'm really looking at the aeration capacity analysis, or I'm trying to study the, potentially the sophistication of my, internal mixed liquor recycle or how the alkalinity is affecting, my nitrification. That's not really a function of what's going on in the clarifier for the most part. I might be fine with assuming that my clarifier is going to work okay. So therefore, I can pick one of the simpler models, just set it and go, and then really focus my time and effort on the biological part. So that's often how I advise people to make a decision about which model you want to use, is if I'm really just focusing on the biology of what's going on, and I'm okay with the idea, or studying just what's happened in the biosolids handling section, and I don't really need to have a predictive clarifier model, then I'd say go for it. Just use the empirical model, set it so that it's removing 95% of the solids, and you're on your way. But if I'm doing more of a holistic, I'm looking at the full plant model, I'm doing a capacity analysis where I want to understand, am I going to run out of clarifier capacity first, or am I going to run out of aeration capacity first? Then I need to have something that's predictive. It's going to tell me when things are good and when things are bad in the clarifier. And in that case, you would use our standard 1D model or the reactive clarifier model, which I'll come back and talk about towards the end of the webinar. Right. Okay. So as I mentioned, if you're interested specifically about what's happening in the webinar, in the clarifier, and you really want to know, you really want a prediction of performance, I want to see for certain loading and operation, what is my effluent TSS, you can use the mechanistic model. I guess I'm just re-emphasizing here that if you're fine with assuming that they're going to have good performance or a given performance, you can set that directly, say I'm removing 99% of the solids and move onwards. And as I mentioned, it saves time because in the 1D models, you have to set a lot more parameters, and you do have to calibrate the settling parameters and so on. And so maybe you don't need to spend a lot of time on that if you know that's not too important for what I'm trying to achieve. Okay, so now I'm going to run through all of these clarifier models and give you a rundown on what the parameters are, what they mean, and give you a sense of what they do. So the very simplest, most straightforward one that we have is called the point clarifier model. It is a model that is a perfect clarifier. It assumes that all of the solids will be captured and go into the underflow. So therefore, the only parameter that is available for you to set is the underflow rate. Once you know that, and we know that, of course, all of the solids are going into the underflow, then we can calculate a flow balance first, and then a mass balance based on that as well. So basically, you'll end up with a 0 effluent solids because it's acting as its perfect clarifier. So there are certain, testing situations, or, if you need to just do some quick and dirty modeling and you want to assume that it's perfect, that's fine. You can go ahead and do that. So the more commonly used empirical model is this one called empiric, and you can set basically 2 of these 3 parameters to define how the flow is going to go. So you can set the underflow flow rate, the underflow solids concentration, and or the removal efficiency, percentage of the concentration that is going through. You set two of these, we calculate the other one, and then by that we can then figure out what is the flow and what is the solids concentration going to the underflow, and then by mass balance we figure out what the effluent solids are. So I find personally I end up most of the time doing these removal efficiency and the pump flow rate at the bottom here. That's the default settings and is the ones that we often use. So basically what it's doing is it is going to adjust the concentrations in the underflow to do that mass balance. Now, there's one more option in the empirical model that you will get when you use the green primary clarifier models. There's yet a third option, which is to use the solids removal efficiency model. And that's one that's, there's all the details are written out in our GPS-X technical reference. And you can find that there. And basically, it's going to say, well, we're going to make the solids capture rate a function of the residence time of the clarifier. And there's some other stuff available for you to calibrate that if you feel like it. So that's available there. Now, as I mentioned, these point and empiric models are good when you want to do just a very quick and dirty setup of a model. Just put them down, assume some sort of capture rate, and move on. But keep in mind that because it's not really there to predict the performance, it's really just to do the solid separation that you need to make activated sludge work. The clarifiers will never fail. It's always going to remove 99% no matter what you put into it. So just keep that in mind. Also note that this lower right connection point is not used in these models. So if you're used to wasting from that section, note that that's actually not used. There's really only the overflow and the underflow. And if you want to use this kind of model, the most common way to deal with this is, since we're not using this one to waste, is to take your RAS, and as you're on the way back to the head of your plug flow activated sludge tank here, run it through a control splitter. The control splitter object is found up where the regular splitters are found. If you scroll down to the bottom of that list, you'll see it there. The control splitter is basically you specify a pump flow rate on one side and all the rest of the flow goes the other way. So it's nice and convenient. You specify this flow rate here to be the sum total of the wastage and the RAS. Recycled activated sludge, and then you can set this to be the waste. You're basically just peeling the waste off of the RAS as it goes back around and sending it on to, well, this is GBT and or whatever other things you got going on your solids handling side. Okay, so back to talking about the different clarifier models. Okay, so we talked about the point, we talked about the empiric model, and then now these two, which are ones that we got from various sources, from WRF and other places. Some other clients had suggested these to us as well. These are there. They're basically that same concept. It's an empirical model. It has a sort of a percentage solids capture rate. But in this case, these are somewhat of a little bit more reactive to the loading, right? So, and they have different bases on which they do them. They're basically just an algebraic equation that comes up with a solids removal based on the SLR or SOR, depending on what's going on. So these can use to make what I would caution you as very rough estimations of clarifier performance, because they do respond to changes in the loading, right? It's not just a constant capture rate that you have set of, say, 75 or 99% or what have you. It actually changes with the loading. And these are good for situations where you would like to have a simple model to work with, but maybe a little bit more realistic. It kind of, I guess you could argue it kind of falls in somewhere in between the regular simple empiric model and our folded mechanistic model. So nonetheless, it's one that's kind of useful and handy, but yet again, I wouldn't rely on it to tell you when the clarifier is going to fail. It's just there to do the solid separation in a somewhat realistic way. Okay, so what I want to do is I want to just jump on in with a simulation here. I'm going to load up a couple of demos that I have put together. Okay, so just to show you our way around what we're looking at here. So open this up here. So you can see here, for example, If I go to the primary treatment section, there's my two primary clarifier objects. And if I go down to secondary clarifiers, these are there. I'm sure if you've done some GPS-X modeling, you've probably played around with that just a little bit already. And here's the clarifier model itself. If I right click and I go to the model section, there's all the different options that we have. Now, for what I'm going to show you right now, I'm going to stick with using the simple 1D model. That's our mechanistic model. So I'm going to come back and talk about that in a little bit more detail later on. But just, I thought I'd stick with the one that's the one you're most likely to use as we go along here. Right. Okay. So let me move over here. So now we can see that this is showing you a regular thing. I'm just going to run a steady state solution here. And there's many things that are kind of handy and to take a look at on the quick pan. So if you're a little bit new to GPS-X, every time you build a model and you put all these things on the drawing board and you build it, it will make a bunch of tabs over here on the right-hand side, and where we collect up and display all the most common output that people like to see. So you can see here, for example, if I'm just drag this down, we have a table of results, and these columns represent these different connection points, these different streams as we go around. So in this case, we have the mixed liquor flowing in. We have our effluent that's going off to the receiving body water. That's this connection point right here. We have our wastage, and we have our RAS concentration. So now I've got this already all set up and kind of running and getting sort of reasonably good numbers here. And what I want to show you is that a really nice way to sort of take a look very quickly and see what's going on in terms of solids removal performance, clarifier performance, is to go up to this display here, click here, and pull it down to TSS. So what you'll see, it's basically this row of the table here, but it's nice to see it in kind of laid out in this format. This is our mixed liquor coming in here, 2733 milligrams per liter coming in. Our clarified effluent here, the overflow going off is 11. And we can see down here the wastage and the RAS are down here at 35, almost, 5367 milligrams per liter. Now you notice these two are the same number. You might not immediately catch that in the sense that these kind of don't look like they're located in the same place. But by default, we are assuming a flat bottom clarifier here. And so these are going to be both taken off the bottom. You have the ability to have a different shape of a clarifier, and you also can specify actually different layers to take your RAS and WAS off if you like to do that. But right now I've got it set up so that they both have the same concentration. Okay, so that's there. You can take a look at all of the other parameters that are here as well. You can take a look at the BOD and the ammonia and so on. So of course, ammonia is a soluble component, so it's the same all over the place going in and out. And I'm going to open up this thing now, and this is our other panel. And this is actually a what I guess you would call sort of like our more specialized parameters. These parameters that you see in the lower panel are very specific and very different from object to object. So here you'll see a lot of clarifier specific stuff. So surface overflow rate, surface loading rate, sludge blanket height, all of those things are key elements that you can display here. And I will note that I'm actually looking at all of this in metric SI units. That's just what I'm normally used to working in. But if you would prefer to work in what we call US units or imperial units, you can just actually click here, and then you can switch this down to be gallons per feet squared per day if you like, or something like that. Just do that and it'll change the number for you as well. So anyway, nonetheless, we see that this particular example that I'm showing you, the water level is 3 meters and our sludge blanket height is at about 0.3. So, you know, it's at 10% of the bottom of the clarifier. That feels like that's doing pretty well. And as I think we saw that already in the sense that our clarifier effluent TSS is only 11, so that's pretty good. And here, if I slide a little farther down, we can see some mass flow. You can see what's the mass that we're wasting, what's the concentration that we're wasting, and other things, you know, useful stuff that you might want to take a look at. Okay, so that's just a quick tour around what we have for our regular clarifier model. Back to the slides. Okay, so I'm going to move on to talk about the background and details that are in the one-dimensional mechanistic model now. So now we're moving on from our simple empirical models, which are sort of fixed removal rates, onto the one that is more of the predictive model. So this is a fully dynamic mechanistic model for doing solid separation. And it's called a one-dimensional flux model because we are actually modeling it in layers, and we have settling of the solids and separation of the solids in one direction. So now it does require more information to use this. You need to specify a lot of the physical details. What is the surface area? What is the depth? And also calibrate the settling parameters. And so I'm going to talk about that a little bit down the road here. But basically, it predicts underflow and overflow concentrations, in fact, a concentration for all 10 layers in your model. And it also is a fully dynamic model. That means it responds dynamically to changes in loading and operation. So you can imagine each one of those layers is kind of like its own little reactor. So we keep track of, first of all, the flow that's coming into the feed layer. So we have like assuming some sort of center well or some way to get that flow into one of these layers. You have the opportunity to dictate which one of the layers is the feed layer. And so we have our flow of solids coming in here. This is the influent plus the RAS times the concentration. So that's flows coming in here. We're wasting some. We have some effluent, and we have some recycle going back. And so the way that we predict all of these concentrations is we break them up into 10 layers, and each one we're doing a mass balance of the solids around each individual layer. So they're numbered. If you are using GPS-X, they're numbered from the top down. You can actually plot each individual layer if you like. And so what we've got in this case is the ability to track the solids. So imagine that mixed liquor is coming in here. It's coming into that feed layer. And we have two aspects that we are keeping track of with our settler model. One of them is the liquid motion. So that is the flow of the actual wastewater, and in this case, at the high concentration of the mixed liquor. Some of that flow goes up and out as part of the effluent, and some of it goes down and is wasted or recycled. So based on the relative recycle ratio, we solve those flow balances first. And then we know that when there's 1 meter cubed of liquid that's being moved up here, it's going up in this direction, it is going to carry solids at the concentration of this layer into this layer. And that does allow us to be able to do a mass balance around all of the flow. And every place where that flow is moving through a layer, it is carrying some solids with it at a predictable level. So that's one part of the mass balance. The other part is the actual settling. So what we're doing is, in addition to this movement, this advective flow, we're also having at the same time solids that are settling. They're flocking together and they're falling from one layer into the layer below it. And the rate at which they fall is a function of the concentration in that particular layer. And that is, in fact, what our settling curve is. It is saying for a given concentration, we are seeing a given settling velocity. We then multiply that velocity by this surface area, and we can get a mass balance of how much solids are falling down from one layer to the next. And so as you'll see in the settling curve, we need sort of a minimum number of concentration, a minimum amount of concentration for flocks to form. And then there's kind of like a peak sweet spot where they settle quite quickly as they're flocking together and falling down into the high concentrations down here. They don't settle as quickly anymore, as it's now kind of into that layer of sludge and compression settling and compaction down there. Right. Okay. So that allows us to do a mass balance around each one of these layers, and we end up with a concentration at each point. So that allows us to do a mass balance. What is the concentration of the solids being wasted and sent back as part of the recycle? And whatever the concentration is in the top layer is what goes out as our effluent. Right. So the settling equation itself is actually a bit of a challenging thing. And so it's got a lot of sort of moving parts to it here. But it is the thing that kind of controls the quality of the settleability of the sludge. So there was previously a very simple sort of sort of curve here that was sort of the early days of settling models. That's kind of the curve that you would have, basically saying that the lower the concentration, the higher the settling velocity. But what we normally use right now is what we call the double exponential settling model. This was actually published by a number of people from Hydromantis, sort of the originator of GPS-X. That was before my time, but these were people who published this double exponential settling model. So that was the original term I just showed you, plus this new term over here. Now that new term has another another exponent on it, and you end up with, here, if I just show you this, you now end up with two terms. You end up with two curves, these two curves that I'm showing you now. And then when you subtract them, you end up with the green one. So that is the actual settling relationship that we are going to use. Now, what this does is it does capture the idea that there's this sweet spot that I mentioned before, that actually things go down as you get to higher concentrations. They don't settle as quick, but at the very high end here, very low end here, low concentrations, the settling isn't very good either there, because you don't have enough stuff flocking together and forming that dense flock that can then settle. So we do, on top of that, apply a maximum settling velocity and a minimum required solids before it actually settles at all. And then, so if I apply those two bounds, ultimately, this is the curve that we are using. So here you can see that there's no settling at all happening here. Like you'll still have the other aspect, the advective term in the mass balance, but you'll say that not really any settling has happened until we get up to this concentration, and then it maxes out, and then it comes down to this end here. And then that now allows us to do the settling mass balances that we have. Now, there are two terms here that can be used that calibrate different parts of the settling curve. We have what we call our hindered settling parameter and our flocculent settling parameter. And they kind of control different aspects of this curve. So our hindered is the one that controls the thickening end. So you can see now we're talking about solids concentrations at the high end of the curve here. And by adjusting this parameter, I can make this line move up or down. So that allows me to make better or worse thickening properties of the sludge. And then the other parameter controls the other end. So this is the low end. So this is the top of the clarifier. And the clarification parameter setting. So I can make it have, I can affect just the aspects of the effluent solids concentration without really making much change in the lower half of the clarifier where the solids concentration is higher. Now, the problem we have is these two parameters actually act in different directions. And they're also very, very small numbers, 0.00051 or something like that. So they're not too terribly intuitive. So, I forgot to discuss compression settling. We have a whole other model down here at the end that we added a couple releases ago that is for compression settling. When you get into very high concentrations, we actually have some other parameters here that will allow you to have better prediction of the thickening at very high concentrations. Okay, so I was mentioning that these three parameters that are hindered and are flocked, and then the total maximum settling velocity, these two parameters are the ones that you want to use to calibrate your model, but they're not super intuitive, right? So what we did was we have a relationship and a regression that allows you to sort of correlate these three parameters with two more understandable and intuitive parameters, SVI, sludge volume index, and this empirical clarification parameter called clarif. So these new parameters are much more easy to work with. And in fact, I use them almost all the time. Their more intuitive behavior allows really for you to sort of have faster and more straightforward calibration. And the only thing is they are specific to secondary clarifiers only. So you'll find that those options are only there for the secondary clarifiers. And basically what we're doing is we're making these three parameters a function of these two parameters, and we have relationships to do those. You can actually read up on it in our tech ref if you want to get into the details. The clarification parameter is very empirical. It basically says you get good clarification or bad clarification on a scale from 0 to 1. 0 is bad, 1 is good, and you can move along in there as needed. And SVI kind of works like the same way that you would do it for measuring it. So just to recap recontextualize all of that. The clarification parameter is really calibrating the top half of the clarifier, and the SVI parameter is calibrating the bottom half of the clarifier. And you have to come in here and turn on that correlation. Use the SVI to estimate the settling parameters. If you turn that on, these go away, and these are now available to you. And it's these first two are the ones that you want to play around with. So one thing, excuse me. One thing I will say is that the sludge volume index is approximate. So we'll see the default value is 150. A lot of the times I'll use something between 150 and 100 in order to get sort of a good starting point for my model. And I usually stick with a default of 0.5 for the settling, halfway between good and bad. This number, you might actually have SVI data for your model that you could start with as your calibration, but I really suggest that it is just a starting point, and don't be afraid to move away from measured values. This is a very rough correlation. And really getting a good calibration of your models is probably better to calibrate SVI so that you match your effluent solids and your effluent underflow solids. Your effluent solids and your underflow recycle solids using these parameters rather than adhering to something that you had measured. Okay. So what I'm going to do is I'm going to say a few words about all the different types of inputs and outputs, and then we're going to go back and take a look at another desktop demonstration here. Okay, so all the parameters that you need to adjust, is just like any other GPS-X object, you right-click on the clarifier itself, go to Input Parameters, and then there's the Physical, Operation, and Settling menus. These are the three main ones that you are going to probably want to touch when you're setting up your clarifier model. So what I'm going to show you now is pretty much only the mechanistic model. This is all 1D mechanistic model going forward here. So the first thing you're setting up is the shape of your clarifier. So by default, we're going to have flat bottom. This is a diagram right out of our GPS-X technical reference. It talks about all the different shapes that we have. And so you can have a sloping bottom that's a little bit exaggerated. Normally, your clarifier wouldn't quite look like that, but idea that you could have a little bit deeper in the middle, conical, circular wedge. This was from a project I worked on many years ago. That was extremely challenging to calculate the volume of this thing. Anyway, that's available for you to be able to use that in the future. You would then also specify, now depending on which one of these things you've picked in this pull down menu here, this one or the other clarifier types, if you go into this more button, you would set the parameters of the size. And generally you're setting surface area and depth. So those are there to do that. You're setting, we're assuming with the regular flat bottom or the sloping bottom one, we're saying that you're setting the surface area, that is of the sidewalls as the sidewalls go down. Basically, we're looking at the water depth. If you have sideboard, like free sideboard above that, we don't really care about that. We're only looking at the amount of water that's in the system. So now, this one particular parameter I have its own slide for because it is a pretty key one that I always want to make sure we touch on. The feed point from the bottom will determine which one of the feed of the 10 layers is the feed layer, right? So this is something that you can adjust as part of the calibration. You would tend to think that the feed point would be the sort of some physical measurement. It's like where you have an opening or the bottom of your feed well or wherever. So that works most of the time, but don't be afraid to have to move it away from the physical location. Particularly, we don't want to have it in the top layer or the bottom layer, even if that's what it's like in reality. What you're really looking at is not so much where's the physical opening, is where are the solids injected. If they come in and then they kind of settle down, or they have some sort of short circuiting or some sort of movement that allows them to kind of be in a layer that's a little bit down or above where the physical opening is, that's the layer that you want to shoot for. Now, what I find, it's typically like halfway up or a third of the way up from the bottom of the clarifier, and typically above the sludge blanket. So even though this feels like this is something you should measure and get off of a drawing, it's actually more like a calibration parameter. So I've had several instances where I couldn't actually calibrate the model all the way with just the settling parameters, and it was because the feed point was really needed to be adjusted. This is also typical if you have some sort of baffling or other things going on in your clarifier that we don't really have explicitly represented in the model. You can adjust and account for those things by adjusting your feed point. Okay. So now that was the physical menu. Now we're moving on to the operational menu. There's lots of different things you can do in the model here. So in this case, we're looking at specifying the pumped flow. This is going to be the bottom right hand side connection point where you would do your wastage from. Typically, you can specify not only the rate, but which layer you want to have it go off of. By default, it will be the bottom layer. However, I've had some instances where the RAS and the WAS were taken off of different layers. You can actually even put on a full PID controller on here if that is the way that you would like to be able to do it. And often if you are doing a mixed liquor controller or a SRT controller, you would set that up in this menu right there in the actual pump connection point of the RAS. You would enter in all of the details, and I recommend jumping over and looking at one of our many process control webinars that we have that describe how to do a mixed liquor or SRT controller. I also believe tutorial 7 or 8, I think it is, in GPS-X also describes how to do that. These model parameters are there to do a little bit of calculation in the background. The sludge blanket threshold concentration is how we calculate the height of the sludge blanket. We actually take a look at all those layers, all those concentrations in each of them, and we find out what is the height at which it passes over the 2,000 milligrams per liter threshold, and we call that the sludge blanket height. We actually interpolate between points. And so there's that. The critical sludge blanket level is basically the sludge blanket height below which we assume that it's completely anoxic. Lastly, we have a state point analysis graph, and these are some of the details that are part of that, and I'll show you that in a moment. So the settling parameters, as we discussed, you've got your SVI correlation, or if you don't want to use that, you can just adjust those settling parameters directly if you like. There you can see that our default values are these extremely small numbers, and our new compression, I shouldn't say new, I guess we've had it for a few years now, new compression settling parameters that we have that are part of the model. We also have a maximum non-settlable fraction here as well. I haven't really talked about that before, but we do assume that there are some solids that come into the clarifier itself, but we just shoot them across and go right out the effluent. You can set this to 0 if you like. It's set to a very small number, 0.1%, but you can get a few non-settlable solids in your effluent as well. And last thing, we have the settling correction factors. So on that settling menu, if you scroll down past all the things I've showed you before, you'll end up here, and these are one for each of the state variables in the model. If you don't recognize these names here, these are the different state variables upon which we are doing the mass balances. If you open up the concentrations menu, and you can see what these names are. The very top one here is really the only one I ever adjust, and that is particulate, inert, inorganic solids. So this is basically your silt and sand and whatnot. What this is a number that we multiply the settling velocity by. And we can see here that we set them all to 1. So that means it's not doing anything by default. However, if you have one particular thing that you would like to be able to make it settle better than all of the other things, you can then do that by coming in here and increasing this to like 1.2 or 1.5 or something. That will make the inert stuff settle better than the others. So these next few parameters here are the different biomass types. So maybe, you know, it is kind of a thing that the Animox biomass is really good settling. That's this one down here, XBAX. You know, you could come in here and change that, and maybe that, you know, because it's a granule kind of thing, is going to be settling better than the others. Okay, so I do want to note that that's basically the same settling model in each type of settler. So it's the same ones in the rectangular settlers versus the circular ones, and it's the same model in the primary, the secondary, and the gravity thickener for the sludge. However, we have different default settling parameters. That's really what differentiates these things from each other. And so you'll notice here that there's different settling parameters, both the maximum and the settling velocity there, and also the settling parameters, the hindered and flocculent zone settling parameters. Those things are different from each other for these different kinds of solids. And so you can come in and override these default settings, but that's how we differentiate the settling behavior in the different models. Okay, so that's all the input. Last thing I'm going to say here is about the output, and I'm just going to run through a whole bunch of different types of output that you can use. And this is actually quite useful because we have quite a few specialty things for clarifiers. So I'm just going to run down and tell you where you can get access to all of these things. So if you right click in the middle of a GPS-X object, as you may know, in many of the objects, the layered ones like the clarifier and the plug flow tank, you can get to other menus that you wouldn't be able to get to otherwise. So if you click in the middle of this, you'll get profiles. This is basically, you're going to get the concentrations from the top all the way down. You're going to get 10 values of total suspended solids, for example. So you can right click there. And then also there's a couple of other things in here too, including the state point analysis graph. If you want to get the concentration of a specific stream, you go to the connection point and do it there. So you won't get any layers, but you're going to get the specific concentration coming out of that stream. So therefore, if you click on the effluent overflow here, this is going to be your effluent solids and effluent concentrations. And also there's other menus up here, including sludge blanket height and some of the residence time and so on. Those things are up here connected to the overflow as well. Right. Okay. So if you go to the output variables menu of one of those places and click on the clarifier variables, you'll find a few other things. As I mentioned, sludge blanket height, you're going to get some, details about the settling velocities and total sludge mass in the clarifier and that kind of thing. There might be useful things here that you might want to take a look at. I did touch on this in the demo that it's really handy if you're looking at a clarifier to flip this over from flow to TSS so that you can have a nice intuitive understanding of what's going on in your model. I'm going to come back and show you on the next demo how to set up this horizontal bar graph. This is basically a vertical profile of your clarifier. So this bar up here at the top is the top of the clarifier. This is the bottom of the clarifier. And the axis on down here at the bottom is the concentration. So basically the farther it goes to the right, the higher the concentration. So this is kind of an intuitive way to look at how much sludge is in your clarifier. So in the very bottom, so these are 10 numbers because we have 10 layers. You can see the very bottom layer has a very high concentration. And then of course, this is your effluent concentration at the top. This is the exact same thing. It's a horizontal profile of what's going on. However, what we're doing is we are just making it darker rather than going from left to right. Some people kind of prefer this arrangement. It's kind of a different way of representing the same information. This one kind of like maybe looks like what you would actually see in a clarifier with darker for the sludge and so on. And the state point analysis graph. So I did mention that previously. If you go to the click in the middle of the object and then go all the way up to the state point analysis, it's going to make a whole new tab for this thing. But then this is dynamically updated while the simulation is going on. So you'll see this intersection point move around as the loading changes if you've got some dynamics happening in your layout. Okay, so a few final thoughts on setting this up. The SBR model, sequencing batch reactor models, also use this same settling model. So with the same secondary clarifier default parameter setting. So basically, if you are using an SBR in addition to all of the other sequencing stuff and aeration and mixing and all of that, there's a settling phase. And so therefore, you also get settling parameters that you can use. And it's the exact same approach that I've just described to you. One other thing you can do is source multiple clarifiers together and have them share one common set of settling parameters. Sourcing is a feature we don't talk about a great deal in GPS-X, but it is very handy. If you have multiple objects on your drawing board and you want them all to share one common set of parameters, so the biological parameters, for example, in the clarifiers, in the bioreactors, or have the same settling parameters in several clarifiers, You can link them all together with this little chain symbol, and only one of them will actually show the settling parameter menu. And then when you do that, it will link them all together. So I'm going to show you an example of that a little bit in a moment here. Also, I would mention that all of our clarifier models are fixed volume. And by that, I mean the clarifier will always assume that it is completely full and overflowing. Right? So if you are in a situation where you would like to be able to pump down a clarifier as part of some simulation and then fill it up again, I would recommend using the manual SBR object, where you can do the same thing. It has the same clarifier model as this one does, and you can basically control it much better. You can have control over these pump connection points. You can empty it out and you can fill it back up again. The SBRs are designed to have variable volume. Okay, so I'm going to run through our second demo now. So what I'm going to do is I'm going to just reset everything here. And I'm going to run now for 10 days instead of just a steady state solution. And then I'm going to flip over and take a look at this horizontal bar graph. So basically, I plotted from this menu here. I went to output variables, I went to concentrations, and I dragged total suspended layers onto a graph. Now that would normally give you a bar graph. I switched it from bar chart over to bar chart horizontal. So what happens is you get that other thing that I was showing you earlier here. So just let me run this. Okay, so now we got a 10-day simulation. You can see here we've got a higher concentration. If I click on the bar, I can see it's 5,300 milligrams per liter. All right, so if I bring in some more flow into this facility, we will see the clarifier start to fill up. So I'm going to do that. I'm just going to increase the flow and maybe put it back down again a little bit. And you can actually use this graph to have a pretty good understanding of what's going on in terms of the sludge blanket. So if I really overload it, you can see the other bars start to come up too, right? So that's the behavior of the clarifier. If I bring it back down again, we can see that it goes back again. So now you can see that same information here just by looking at the effluent quality. So this is now the top of the clarifier. We can see as I was moving that up and down, and I really pushed it up there at one point, the effluent solids also were going up, and this is was tracking that. But nonetheless, I also like to have this. It kind of gives me an understanding of what's happening. Okay, so what I'm going to do is I'm going to stop this for a moment. I'm going to reset everything, and I'm going to put this at 4,000. And now I'm going to talk about the settling parameters, which I've put on a different tab over here. This is the SVI and the clarification parameter that I was mentioning before. So now I'm going to run that simulation again, and I got it at 4,000 meters cubed per day in terms of the influent here, just because I want this to be a little bit challenging. So now what I'm showing here is I have this sludge volume index, so 100, right? So that's pretty good. SVI, reasonably, SVI, let's say. And so if I change it though, we'll see the change here immediately in these solids. So if I were to increase the SVI, what that is saying is that you are now getting less settlable sludge. So if for some reason that sludge became, had very poor settling qualities, this is what would happen. You would end up with not as high concentrations at the bottom of the clarifier. So therefore, you might get the actual bottom layer might go down in concentrations, and some of the ones that were in the middle, which were previously low, are now not getting all the way down. Your solids are not getting all the way to the bottom of the clarifier. So let's bring that back again to where it was, and that kind of preserves our situation. Now, if I want to take a look at the clarification parameter, that's dealing with what's going on in the top, and the scale of this graph is pretty tough to see. So actually what I did was I put effluent solids, this black line here. So you can see even adjusting the SVI was affecting our effluent solids. But here, the clarification parameter, it's a pretty straightforward relationship. So if I increase this towards the good side, then the effluent, it is now the clarification is better. So therefore my effluent TSS is lower. And if I had bad clarification, it would go the other way, obviously. So these two parameters are fairly nice and straightforward and easy to understand about how to calibrate your clarifier model rather than dealing with R hindered and R flock and Visual settling velocity directly. So now you obviously have the both. If you are really interested in the details of how it works, you can welcome to use the other one, but turn on that SVI correlation. That's the one that we would typically use most of the time. Okay, so that is talking about the calibration process, calibrating your clarifier. Right, so let me go back to my slides. How am I doing here? Oh, I'm getting pretty close to the 3 o'clock here, but we're going to keep going. So the last thing I wanted to talk about was the reactive clarifier models. By that, I mean it is the simple 1D settler model, so the dynamic mechanistic model with the 10 layers, but each layer also has a biological reactions in it as well. So each layer is then treated like a completely mixed tank, and it assumes no aeration, and then we apply all of the biological model as well. So you must then use the sourcing function of that clarifier over to a bioreactor somewhere, like the aeration basin, so that they use one common set of biological growth rates and half saturation coefficients and so on. So that's a nice way to set that up. I will say it does make the model more complex. Now, if you think about it, what you're doing is it's kind of like putting 10 more reactors on your drawing board, right? So it is mathematically much more complex to do that than it is to do just the simple solid separation. But there are many situations with regards to the anoxic biology that may or may not be happening in your clarifier, such as denitrification or hydrolysis, that is there. And so if you need to capture that, you need to flip it over from simple 1D to the biological model like Mantis 2, so that it is doing both things. So as I mentioned, it's computationally more intensive. It might take a little longer to get to steady state, run a little bit slower, but you are running like an order of magnitude more complex model when you do that. That's why it's not the default setting. Okay, so I set up an example of that as well. And so one thing I'll very quickly mention, just because this is the regular simple 1D model, right? So if I look at the simple 1D model, if I pull this down, just as a moment of comparison, if I look at nitrate here, note that basically it's the same number going all the way in. All same number going in is the same number going out. So there's no biological reaction that is changing nitrate here. So what I'm going to do is I'm going to flip over to another model that I created. And this one's I made this one a little bit simpler. I didn't put the biosolid stuff on this one. However, if I go here and I look at this model, I selected the Mantis 2 model. That's the same biological model that's being used here in the bioreactor, right? So in order to build this model, I need to now source this over to this model. So sourcing here is where I want to link biological parameters. And I want to link to the plug flow tank with the label AER. That means these are going to have the same sets of biological parameters. So if I increase, an AOB growth rate in here, that's also going to be increased in the clarifier as well. Okay, so once you link that, you'll see this little chain thing on the top. Now, if you actually had multiple different clarifiers, you could link them all to this bioreactor. And in fact, you can even share settling parameters amongst these things as well, in which case you would see another chain showing you that they're linked to other parameters as well. So, but if you're ever curious, if you go back to that source data, it'll tell you which thing it's linked to. Okay, so now we're going to go over to simulation mode. Now I made a change there, so that means that it's going to rebuild the model. So while that is happening, I'll just tell you what's going on in this layout. This is basically a more or less straightforward nitrifying activated sludge plant with a plug flow tank. I set this influent up to be a little bit challenging. It's got actually a fairly high. It's got a TCAN of 50. Ammonia of 35, and the flow is 2,500 meters cubed per day. So that's a little bit big for the size of this plant, but I kind of wanted that sensitivity to be able to show you what's going on here. And I made this clarifier a little bit deeper than the default as well, just so that we could get a little bit more residence time in the anoxic behavior there. Okay, so everything's set up and we're ready to go. And so I'm going to run just steady state for this one. And let's go over to the clarifier panel here. And So if I, first of all, as I mentioned, you can go and flip this over to TSS so we can see there's our mixed liquor, almost 2,100 milligrams per liter. We got an effluent of 16, so that's not super great, but okay. And, we're doing reasonably okay. But what I actually wanted to talk about was the nitrate, because I want to show that there's actually denitrification happening in this secondary clarifier. So instead of just sticking on TSS, I can slide down here, go to nitrate, and we can see it's 28 coming in, right? So it was 35 coming in the front end of the tank, of the plant. And so we are getting full nitrification and a little bit of denitrification probably along the way somewhere. And we can see that it's 28 in the effluent here as well. But note that at the bottom of the clarifier here, it's 23. So we've lost 5 milligrams per liter to denitrification in here. So you can actually see that in the table here as well. But that's kind of a nice way to see that the nitrate at the bottom is not the same as the nitrate in the effluent. And so there's some stuff going on. Now, one really cool thing that you can do is to look at all of the individual biological processes that are going on. So in the same way that you can right click and go to the output variables and go to the Mantis 2 rates biological model, you can see here that these are all of the rows of our matrix of reactions that are happening here. So we all have all of these different kinds of things going on, all the different growth rates with different substrates and all the different biomass types and so on. So now you can also see those in the clarifier too for each one of the layers that are happening. So normally if I go and I don't see this Mantis 2 rates here, you have to be using the biological model, reactive clarifier model, and I can do something like look at anoxic hydrolysis. And I can look at it at all the different layers of the model. So here at the top, we're getting like some negligible amount of anoxic hydrolysis, like 1 milligram per liter, so that's nothing, until you get to the bottom. Down here where the sludge blanket is, look at that. It's like 3 orders of magnitude bigger down here, actual hydrolysis of the slowly biodegradable substrate, making it into readily biodegradable substrate. So there's actual biological activity happening there. And you can do it as well here. If I want to talk about that denitrification, I could look at this one, anoxic growth of heterotrophs on soluble substrate using nitrate. Here, again, nothing much happening at the top, but down at the bottom, we've got some pretty significant growth down here, anoxic growth of heterotrophs. That's doing denitrification. I can even look at if I slide way down here, down to the gas transfer. So if I look at gas transfer of N2, so that's now denitrification, that's releasing the N2 gas. I can look at that number. Now, these are negative because the way that our derivatives are written, the gas transfer going out is negative. If you were transferring oxygen from an aeration system, that would be positive. So here we're saying this is the release. And we can see, again, it's in that bottom layer. There's some significant things going on there. Now, I have one last thing I should mention about this. Because we are releasing nitrogen bubbles here, this does not directly affect the settling. This is a question that comes up a fair bit. So note that even though we're actually having biological activity and we're releasing nitrogen gas, which would release in some bubbles and probably have an effect, there is no model to link the settling parameters to the behavior of the gas transfer here. So you can explicitly say when this is happening, I'm going to make the settling a little worse, but it does not happen automatically on its own. And that is something that I really wish that somebody would publish models like that, and we can eventually include that in GPS-X someday, but we have not seen an industry-wide accepted model for that yet. Okay, so I will mention it. Now, that doesn't mean that you can't use this to analyze that exact problem. And in fact, one of the very early industrial wastewater modeling projects that I worked on at the very beginning of my career, I think within the first year when I started, was for a brewery, and they had very specific problems with denitrification in their secondary clarifiers. And we used this reactive model, and we monitored this number. So during different loading periods, and during different operational setups, we were able to predict, these were the risky times when you're going to get some of that. And we did it by modeling how much gas was being transferred, even though we didn't explicitly change the settling parameter. Okay, So there you go. I think that's a fairly lengthy thought on how all of our clarifier models work. Just to wind up a few thoughts, basically that diversity of different types of models from very simple to very complex is there for you to be able to meet the needs for your project. And I always suggest just use the simple model as possible for the task at hand. And our simple 1D regular flux model is very, very good for almost all applications. It's really good at steady state, and it actually is reasonable for doing dynamics things as well, although we do recommend you calibrate the model with dynamic data if you're going to do that. And it's the one that is used most of the time.